about homework eventually. But we're doing right now. Okay, if I were you, if you want to feel the pain, because Maggie did ask, how do we know? And I don't know. I feel like with most of math, it's trial and error, right? Seeing sometimes it works and sometimes it doesn't work, and which one happens when. So I wouldn't write it down unless you want to feel the pain of how would we approach this integral. The way I thought about it, and I was saying it, that some of you might have been following and some of you, it was a little too much. I thought about this with throwing in the integral that we do know, because this would have been arcsecant. One over a, right? Arcsecant of u over a. Okay, because then we could have done, because x squared is always a positive, so making them both absolute value wouldn't change the meaning, right? X squared is always positive, so absolute value times absolute value always positive. I think we're okay doing that, mathematically speaking. Yeah. Or we could have restricted the domain. That would have been pretty good. So then we would have had to have absolute value of x to the negative 1. So that'd be negative 1 over absolute value of x squared is just x squared. They're both always positive, times u prime would be it's not in the integral? It's in the answer? How did I miss that? Oh, I haven't done it yet in AB this year. Is that why it's not in the book? Only on the answer, not in the original expression? I wonder if it would flip if it was the other way, and that's what I'm remembering. Sorry, I'm questioning your forever cards, which is dangerous, right? Where would that be? Trig sub? No, trig integrals. Inverse trig? Yeah, I remember there was something weird. I'm trying to get a textbook instead of like a what I did. Because as we all know, am I perfect? But I think I did change it last year to be correct. Where's the inverse trig anyway? Yep. Lame. Which actually makes our life easier because I don't have to worry about that. But thanks, Riley. And friends. So that's going to be a normal x. That's going to be a... Don't need the plus c because we're doing the other. So dx can come over here. I don't know about you guys, but like this is feeling pretty good. Besides the whole like I don't know the rule. as far as like, okay, like we were able to anti-derive one, derive the other. And it feels like a loopy one, kind of, right? Because the next one, as we go ahead and take the integral, I guess I could pull out the 1/3 and then the negative. So I could do negative 1/3 integral of, now I'm going to have 1 over x squared arcsecant of absolute value of x over 3 dx. Like I have two different pieces again. And with the two different pieces, if there's an arcsecant, the only thing I can do with it, Liate logarithms, no. Inverse trig, yes. We always have to make do the inverse trig if there's not like a u prime weighting. So then we'll go ahead and make our u the arcsecant. Because it feels like a loopy one. So then we have our 1 over x squared. Our v is going to be, oh, sorry. I'm not doing lucky 7. We were just talking about this too. Ariane, you were in here. dv is equal to 1 over x squared. V is equal to negative 1 over x, right? And then du is equal to 1. I can do square. Which would be the same thing as that, which we would end up with. It looks like it, right? Hold on. Where are we at? Ugh. I'm going to write down here. Plus 1/3 uv, so negative 1 over 3x. See it? Minus a negative should be a positive. Do you see it? Wait, hold on. No, right here. My bad. My u prime was weird. Because I need to deal with the 1/3 and the actual derivative. I was just being lazy. Yeah. Or it'd be x 3 over x. That would technically be 1 over u square root of 1 minus u squared times u prime, right? The derivative of arcsecant. I was trying to do the u's and the a's, and I don't think my derivative went well with that. So that would end up being the 3's reduce, those reduce, 1 over x square root of, that's going to be x squared over 9, common denominator 9 minus x squared all over 9. That's going to pull out a 3. That's going to flip up on top. So therefore, this should have been 3 over. Ugh, I forgot my A. Ugh. Ha-ha. There we go. Oh, I didn't. I had to write it out. Oh. I didn't do all of it in my head. I just kind of figured out, and I thought I was right, because I know that works. Anyway, coming back. Ta-da. I pretend to know things. Sometimes I don't. Something like that. Where are we at? So then the 1/3 and the 3 would cancel out. That'd be a plus. I would subtract, and I would get 0. Did I make a mistake here too? Yeah, that's what I'm looking at. Where is that from? Oh, haha. U, V, from... Because I'm dumb and I distributed the 3 when I shouldn't have. Oh my goodness, we should sue. There we go. So then the negative 1 over 3x and positive 1 over 3x. Ha! How'd you like that answer?
Not a lot.
How do you like them apples? What do they tell you? Something's true, but what? Can we delete that page? Sweet. So, hey, there's a how page. If you want, you can start with the how page, then we can come back, or we can just try to do this one. What do I see? I see a little baby Pythagorean and a nasty problem that nothing else was going to work. An integration by parts would have sent you on a wild goose chase. And if you did it right, well, if you did it wrong, it would have looked like it worked. Anyway, struggle. But I see a baby Pythagorean where the hypotenuse could be 3 and the opposite could be x. And the adjacent would be square root of 9 minus x squared. At least from yesterday, did we see that we're working with a squared plus b squared is c squared in some way, shape, or form? So as you guys are pondering that right triangle and maybe thinking about what trig stuff we could work out, remember, what we're doing is there's strategy to that, and I haven't fully explained it yet. But in general, if possible, the variable goes with the opposite. In general, if possible. Like if it was x squared minus 9, x would have to be the hypotenuse. Like there's no other way around it. Because, sorry, here's what I was showing. All these different rearrangements. C equals square root of a squared plus b squared. So if you have a plus with squares under a square root, that's going to be 2 legs, right? If you have a squared equals c squared minus b squared, if you have a minus, then this one's always the hypotenuse, and this one's always a leg. And the strategy in general, when you're setting up, if possible, make the opposite with a variable. If possible, make the opposite with the variable. And everything else just kind of falls into place. So what I did is I saw, okay, 3 had to be the hypotenuse because there's a minus, so that's c squared minus. Okay, you have to be a leg, and if possible, I'm going to put you in the opposite spot. He could have been I make it opposite instead. Now, yesterday you guys saw me for just a second being like, okay, let's go right now and plugging in. But then I was like, oh no, dx! So instead of trying to like figure everything out right now, I'm just going to be like, I need dx, which means I need to take a derivative, which means I want the simplest expression possible. That's the simplest expression possible. Anything else, tangent or cosine or secant, I guess you could do cosecant. Ugh. Sine's the easiest expression, like the easiest trig with the simplest fraction. And why am I doing that? Because I need to somehow, if I'm going to go putting in thetas, I need a d theta, which means I want the simplest thing to take the derivative of. If I take d theta, if I take the derivative of both sides, I'll get cosine theta d theta is equal to 1/3 dx. Whew! That's an easy expression for dx. Anything else, if I had used any other trig, would be a nasty dx expression. So then I could go ahead and move 3 to the other side. So now I have an expression for dx is equal to 3 cosine theta d theta. And that's all well and good, but that's just the dx. What else do I need to do? So now we have options. One option is exactly, we could come back, we could solve for x. And we could just say, fine, anywhere there's an x, I'm going to plug in and then I'll do my trig stuff. Or if you see an expression that somehow matches, you can try to make it a trig expression. We could make this 9 minus 3 sine squared and then make that 9 minus 9 sine squared, then make that 9 times 1 minus sine squared, which is 9 cosine squared. Or we could just say, hey, wait a minute, isn't this over cosine? So I mean, we could actually make another expression and be like, well, we also know that cosine of theta is adjacent. So you could kind of go trying to match things and be like, hey, I have something for him too. The other way would work, just you're going to have to be playing with Pythagoreans, etc. in that 9 minus, and then you have the sine squared-y thing, and then do some factoring and do some Pythagoreans, and then do some square rooting. When we go to plugging in, because now the name of the game is we have to get the dx in somehow. I'm going to go ahead and say, hey, I have an x guy, so let's go ahead and square him. I was able to get what this equals, so let's plug in him. Once you get trig in, you can start playing. Like, oh, hey, that goes away. And oh, hey, that's 9 sine squared, so the 3 over 9 will be 1/3. 1 over sine squared is cosecant squared. Oh, thanks, I didn't even see him. Gracias, that's a 9. Yeah. There you go, that's nicer. That's nicer. Yeah, no, it was my bad, I did some illegal stuff. Cosecant squared's easy, right? Maybe not for all of us, but cosecant squared comes from a negative cotangent. I'm done! But I'm not. Yeah, 1 over sine squared is cosecant squared. Trig sub, your t-proof skills come back to play. What's the problem with that being the answer and why I can't stop? It has a theta, and it started with x's. The same way with u sub, they have u's, and I need them back to x's if I'm solving the indefinite integral. But that's okay. I have a triangle. And you know trig, right? Joshikao. Adjacent over opposite is cotangent. Oh. Plug it in, done. Negative 1/9 times x over square root of. It's a struggle. It's a Friday. Thanks for all the grace, guys. Adjacent. That's tangent, kiddo. That's what I did. So take your tangent and flip it. Don't you dare go crossing out 9s, but besides that. Dun, 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 dun. I don't know. It would kind of be like a kitten and a puppy all at the same time. Actually, just be bad math, because he's under a square root. You can make it 3 minus x. That's killing a puppy. The 3 and the 9, and then... But this speaks... But this speaks to how good your middle school training was. Because you guys are like... And I see so many weird things. It's a struggle. So clues, steps. Let's stop talking about how bad some of our kids' mistakes are. Anyway, not the kids themselves, just their mistakes. Stick to sine, tangent, and secant. That's my advice, but you guys see I was playing all over the place with like cosine and then eventually cotangent, and you're playing with the triangle. That's really what you're doing. But in general, this whole sticking to sine, tangent, and secant is the reason why we try to put the variable in the opposite. Sometimes it has to be hypotenuse if it comes in this spot. Otherwise, if it's a leg, we put it in the opposite spot. It basically gets us back to easier. Set up triangles, right triangles, using those relationships. For x, that way your dx is really easy. That's why then going straight to match. Something simple. There's my x, yay, dx, and then go looking for what's left or what's going to be left. Solve basically using T-proof skills and trig identities and transformation techniques and legal math. I don't know. If possible, and then get it back in terms of x. The one is if it's definite. Maybe you could change the x bounds to theta bounds and just solve it as is. But if you do change x's to thetas, here's a struggle. You're plugging in and doing sine or cosine or tangent inverse, and then all of a sudden domain becomes a mess. Because we'd have to be really careful with which angles we actually use. So it's not impossible to go to theta bounds. It's just tricky because domain becomes a problem whenever we go to inverse trig. Yeah. Here's the dilemma. I could remind you of the restrictions, but I'm just saying domain is a mess because technically your expression doesn't force the inverse restrictions. You use inverse in your calculator, for instance, to get an answer, which that answer is held within certain restrictions that the original expression will not have forced upon it. Which means, based on the actual x values, you might need to think outside the inverse restrictions. Does that make sense? I think I might have a definite one that we can play with somewhere. I might not. Oh, hey, there's a whole table. Let me see, Aryan, if I have an example first. That way it'll make a little more sense rather than just going straight to the restrictions. The problem wouldn't be your trig being able to solve because you would be putting like thetas and theta bounds in terms, because you're going to be using the x's, because you don't want to go looking for theta in your calculator. The problem isn't that the calculator can't solve it. The problem is whether you would get the right bounds for the calculator to use. Does that make sense? Okay. You do not have to write this. And I don't even know if I would necessarily make you memorize it if this was an actual unit. I would probably have you write it down if it was an actual unit and if it was on the AP. It could be helpful for some of you, but the long story short, can you guys tell that the x, as much as is possible, is the opposite side? The variable expression, as much as is possible, is the opposite side. Sometimes, if it comes first in the subtraction, it'll be the hypotenuse, so our hand is forced. And if that's the case, well, we just keep the a in the adjacent like he usually is. As soon, though, as we start writing down, like, hey, think this with trig, there's always a problem that'll throw you for a whole, like, whoosh, and then it's not really what you think it is. So this one does say, hey, let you, but if you're in CalcBC, I think it's easier just to say, make a triangle and pull out what you can. Since it's not a unit, since it's not a test, since this actually won't even be on the Chapter 9 test for you at all, it's just kind of a quick aside in the worksheet and we're done. Let's not stress about the table, but it's there if you want it. Does that make sense? It's in the notes, it's in the video. It's there if you want it, if you want to try and use it. This one already did. Why is there? I like that idea. We have time. Go grab a whiteboard and marker. I don't mind. Because your groups are going to be done by the end of the week anyway, so let's go ahead and use it one more time. Uh-huh. Mm-hmm. Oops. I did not take away these solutions from last year. Oh no, what I do? Oh, I do have a definite integral one. Sweet. Ah! Someone wrote on the whiteboards that are meant to be written on. No, are you serious?
Yeah, they wrote, you got this.
Well, ready, set? Let's see what you can do. If you have the marker, don't you dare monopolize the whole thing and ignore your group. Be talking through each and every step. Issue. If you want to pause and ponder how bad normal U sub would be, you can, but it would be bad. Just think like your U sub, how when you take U equals du dx, like it's separate, you can think similarly to that. So the derivative of x is like 1 dx because the d theta will be on the other side. Does that make sense? Can I start playing just a little bit? A little bit.
You don't mind? Are we read so far? And if so, is the next step parts?
Ooh, isn't it tangent? That's x over 1.
Oh, yeah. Yes.
Okay, that helps so much more.
With the 3 halves? Yeah, the 3 halves is nasty. But see, I always think of these as fractions, so I think of it as 1 1/2. So there's 1 whole 1 and a square root. That helps my brain. If you guys haven't peeked at the board, I just kind of got you started. You might go a couple different directions, but should be pretty close.
Okay. Things are looking up. Things are looking up for us. So, there's no way this is right. There's no way.
Oh, you brought it.
What?
Wait, what? Maybe just is negative? Cosine is derivative.
Mm-hmm.
Wait, do you guys have negatives? Or yeah, it's not.
Derivative is positive cosine.
Oh, yeah.
Do you get it? Does it make sense, Carrie?
We were close.
Do it. I'm just trying. So secant. Or we could have done the 3 halves, but I don't know. I still don't like the 3 halves. Yeah. The other you could have done.
It's upright though. That's good.
Yeah. You could have done it
I know.
that way, if that makes more sense. 3 halves.
I got all confused.
Yeah.
We're like, if you put it into the triangle, right?
Is it making sense? Oh, yeah. Because it's a square root. That's why. Yeah. So if you had your square root, then it would have worked out okay. Isn't that kind of crazy though? Like algebraically, you can't play with this. Like there's nothing to do, but trigonometrically,
So weird. It makes more sense now.
if you're ready, in your groups.
Another one?
Oh no.
Oh dear.
Oh, what is that? What is that?
Oh, it's a definite. Oh.
It's a tough.
Oh gosh.
You were asking for it.
I was asking how to do
Alright,
it.
That's okay. To do a definite, you have to try an indefinite, right? Or start with an indefinite.
Can we just use our calculator?
Party poopers. No.
On the exam, could we just use our calculator?
Yeah.
no way that there's no way that this must have like that would be so
Unless it was on FRQ, like that someone in another calc class could have done by hand, but you guys, it's on the calculator. You know what I mean? 'Cause there are some integrals that they have you do in the calculator that could have done by hand. But. Start indefinite. Don't worry about the definite. Take away the bounds if you want. Issa, does it make sense? They're thinking about this. Like they're thinking which one. And then they're going to go ahead and go to 10. Yep, one of the legs is going to be square root 3. So it's x squared.
Wait, is it square root 3 for this one?
Yeah. Yeah. The same way you try to keep the variable, I should write that. You try to keep the variable opposite and the constant down.
Oh, no, you're right.
Oh wait, no. It's
Oh, it's gonna have an LN. Oh, no, never this. Never this. Oh my goodness. What would be the flag? So we've seen this kid. All the way.
no. That's
Oh yeah, she did. She did see.
no, we're good.
Oh, wait.
Biggest one. Well, biggest one.
So, should I just this is what I did before. Yeah, we can grab that. Grab this. Yeah. But then it's just like back to wrap.
Those are things that I'd be considering.
Oh, because we set up our triangle different. No, so technically, we put the
You could be right.
there, and then we did.
Could be right.
Okay.
Just generally cosecant gets a little hard, but you could. Yeah, it's legal. So that makes, but that's why I changed this Because I said try to keep the variable, but you had to choose the. So in general, it's easier if you keep the constant.
Because
I took the derivative, yeah. Oh. Thanks, Riley. You saw the illegal part, right?
You're doing great.
I didn't write the d theta.
If it was cotangent, then you could have done like the sines cancel, and then you have secant times cosine, which would have just been 1. That would have been so much easier.
Oh, you meant if the problem was a little different?
Yeah. But there's nothing that would have produced secant cotangent. So
yeah.
Well, 1 over cosine, cosine over sine. The cosines could have reduced.
then we have this. Cosecant is
What is that?
hypotenuse over. Oh, okay, so then it would be this over this.
Wait, isn't this or
Well, technically it's done. That is sick. Wait, someone else.
yeah. I mean this is also negative, so we got rid of the negatives, but we forgot to say that. But all was true last time.
You ready? No, I'll just go for it. Can I go for it?
It's kind of complicated. Yeah, because then that would cancel. But then we have all of this. Pros and cons.
Oh, no, we're wrong.
Oh, wait. Oh, yeah. Because this is 1 over cosine, right? So then this is tangent. So then this is tangent squared, grad, wait. I feel like I did this right. Because then you have, and then what's the integral of tangent squared? Isn't that one of our? Miss D, can you integrate tangent squared?
Nope. So you make it secant squared minus 1, and then you can integrate.
Oh, we need a band.
Ooh, pretty much it's over.
We got 1/2. Hold on. We can check this though, right? Because what did you guys say we could have done at the very beginning?
Oh, we checked in the calculator. It's like 0.093.
1 minus root 3 times pi. What was it, Maggie?
Like 0.093.
Bye, guys. Check it out. It's on the video. It's online. See what you can do. P.S. There are thingies that some people would have somebody, I don't know, somewhere memorized, but we're not going to. P.S. Worksheet, only try the odds. I'm going to post on Google Classroom the solutions to the worksheet. That way you guys can come in Monday with a fully informed set of questions. Sound good? All right. Bye, guys. Only the odds on the worksheet practice problems. Otherwise, it's going to take too long. Way too long.